What's up, my people? So, the ideal gas law is what we're going to talk about today. The ideal gas law pertains to a gas when all of the gas variables are changing. So, we can use uh, pressure, volume, moles of gas, and temperature to find an unknown. Okay. So if we have three of those, we can find one of the unknowns. R is called the gas constant. And we're going to talk about where R comes from in a second. So the first thing, so I want you to familiarize yourself with PV equals nRT. That is one of the really foundational equations that we're going to be talking about. This is called the ideal gas law. The pressure times the volume equals moles of gas times the ideal gas constant times the temperature. Okay, so we're going to do one example problem. It says a deep underground cavern contains 2.24 times 10 to the sixth liters of methane gas at a pressure of 1.5 times 10 to the third kilopascals, okay, and a temperature of 42 degrees Celsius. How many moles of CH4 gas does the cavern contain? All right, so here's the deal. Right here, we have two different values for R here. This is the one that I want to use. So we're going to have to do some conversions, okay, to go from kilopascals to atmospheres, okay? So we're going to write down our givens. First things first, right? Always, if you have an ideal gas problem, always R is equal to 0.0821 liters times atmospheres. And yes, I want you to write the units over moles times Kelvin, okay? We're also given the volume. The volume is 2.24 times 10 to the sixth liters. Okay, we're given the pressure is 1.5, or here, pressure is equal to 1.5 times 10 to the third kPa. All right. And then the temperature is equal to 42 degrees Celsius. We are trying to find N. N is the moles of gas. So N is something that you always, and you know that if you're finding N, you're finding the moles of gas. Now, there's a couple conversions we have to make. We talked about last time. Temperature cannot be in degrees Celsius. Temperature needs to be in kelvins. To go from degrees Celsius to kelvins, we always add 273, okay? So 42 degrees Celsius plus 273 is going to equal 315 kelvins, okay? And then remember, I said kPa. We are going to convert kPa. And this really, the reason why I make you do this is just to get some extra practice with conversions, because I think it's important, okay, to know your dimensional analysis. So this is 1.5 times 10 to the third kPa. We said earlier that 1 atmosphere is equal to 101.3 kPa. Okay, so 1.5 times 10 to the third, that's 1500 divided by 101.3, and you're going to get 14.8 ATM. All right. Now, the next thing you're going to do is we're going to write down our equation. PV is equal to nRT. Okay. What are we solving for here? Our unknown is moles of gas. So we're going to do some algebra here. N is equal to, if I divide by RT on both sides, I get N is equal to PV divided by R times T. And so that's going to, now I just got to plug everything in. 14.8 ATM times the volume is 2.24 times 10 to the 6th liters. Okay, then we're going to divide by 0.0821 liters times atmospheres over moles times kelvins. And then we're going to we're going to multiply that number by 315 kelvins. Remember, your temperature is always in kelvins. And we're going to end up with N is equal to 14.8 times 2.24 times 10 to the 6th divided by 315 divided by 0.0821. And we are going to get 1,280,000 moles. Okay. Yeah, that's about right. That's a lot of moles of gas in that cavern, but we are talking about, I was a little confused at first, then I remembered that we're talking about a whole cavern, so that makes sense for there to be a lot of moles in that cavern. Okay. All right. So now, where does R come from? We talked about R, that's called the ideal gas constant. R is the ideal gas constant, okay? R comes from the fact that STP, okay? STP stands for standard temperature and pressure. Okay? And Avogadro's law states that 1 mole of gas at STP is equal, occupies a volume of 22.4 liters. Okay, STP, standard temperature and pressure. The actual numbers for that are 0 degrees Celsius, which is 273 kelvins, and 1 atmosphere of pressure. So the temperature is 0 degrees Celsius, and the pressure is 1 atmosphere. Okay? So Avogadro's law states that 1 mole of gas at STP occupies a volume of 22.4 liters. So from that, we can figure out the value for R, okay? Because we know that from the ideal gas law, we know that PV is equal to nRT. We can do a similar manipulation of this equation as we did in the problem beforehand. And so we're going to get R is equal to PV over NT. If I plug all those in at standard temperature and pressure, the pressure is 1 atmosphere. It says that the volume is 22.4 liters. And then the moles of gas, it says 1 mole of gas, and 1 mole of gas at STP. At STP, we have 273 kelvins. Okay? So all I really have to do here is do 22.4 divided by 273. And I get 0.08205. And then liters times atmospheres over moles times Kelvin. Okay? And I just round that to 0.0821 liters times atmospheres over moles times kelvins. Okay? And then, so that's where R comes from. Then I want to talk quickly about the density of a gas. Okay? We know that the equation for density of a solid or a liquid is mass over volume. Okay. We get a poem from John Hale. All right. We also know that PV is equal to N times R times T. All right. So how can I solve for the density of a gas? All right.